So this is roughly where we stopped last time. So we were able to do prediction. And I said that in general, we're going to think about two problems, prediction and control. So what we demonstrated, or what we looked at last week, was the ability to estimate the value function of a policy. So that's the expected value of a policy. But we know that's not enough, because this only tells us how good a particular policy is. It only tells us that given a particular policy, this is the expected value. It doesn't tell us whether that's the best policy. It doesn't tell us what other policies exist. So we now need to think about exploration to find a new policy. So ultimately, what we want to find in reinforcement learning and in planning in MDPs is the optimal policy. The optimal policy is the best policy, right? Optimal means best. And optimal typically means best with respect to some explicit metric or measure. And for us, the optimal policy will take the best action in all states. And the best action means the action with the highest Q value. Okay, just like it does for this is the Bellman optimality equation. So the optimal policy is the policy that takes the best action in all states. So in order to find the best action, we need to compare it to all the other actions, right? If I don't know a value or I don't have a value estimate for the other actions that are possible, there's no way for me to say whether this action is the best or not. And that's really different from the value iteration case, right? In the value iteration case, when I run value iteration, I get a Q value for all actions in all states. So when I do Q values, when I do value iteration, I know what the values of all the actions are, so I can choose the best action. In reinforcement learning, the only way, so if you remember the previous slide, the only way I get any information about an action is by executing it in the real world. So I need to get those estimates, and the only way to get those estimates is to execute them in the real world. And that can be problematic, right? So if I was optimal, there's only one action that I would be executing in every state, because that would be the best action. Well, there may be a collection of best actions, but in general, I want to only execute the best actions. But in order to know that these actions are the best actions, I also need to have tried all the other actions. And this is what's known as the challenge of exploration versus exploitation, right? So exploration, the bottom, is executing non-optimal actions, or any action really, to gather data. And that allows us to tell which is the best action. And exploitation is gathering reward now. And this is really crucial to reinforcement learning, because in reinforcement learning, I am in the true environment, right? My robot is moving around, doing things. And if all I do is explore, then I'm probably a very bad robot. But if all I do is exploit, then I've got no idea whether I'm actually being good or not, because I've got no information on the rest of the policy. The sort of classic, or the sort of standard way of making this trade-off is to create a single policy that is parameterized in order to do exploration versus exploitation. And this single policy way of doing it is typically done by creating something called an epsilon greedy policy.